Okay guys, how are you? I hope all is fine. I welcome you to my channel, which is Industrial Project Management, and we are actually dealing with the thesis, the extract parts. We are dealing with the research papers, the conference proceedings. We are dealing with journals. We are dealing with scholar papers, citations available already on the Google, but just to give or enhance our channel, we are actually producing videos just on our own to help you guys and also to improve the growth of our channel and also the presentation. With the help of this extract, which is about the separation control on high lift airfoils via micro vortex generators, John C. Lynn, Stephen K. Robinson, and Robert C. McGeeth. It is NASA Langley Research Center, Hampton, Virginia 23681, and Walter O. Valeroso McDonnell Douglas Airspace, Long Beach, California 90846. So that's the PO. So we're going to actually just read out the extract. If you are interested to get the further material, you can download and get the soft copy from the system or from the computer as well. But if you are interested, you can ask for the soft copy on request. And obviously, if there is a payment required from the author, you need to pay, and obviously we can arrange for that as well. But right now, we are just actually what we are actually making you actually aware of the extract on the aerodynamics, which is actually our field, as well as far as the entrepreneur skills are concerned. An entrepreneur ultimately dealing with the different industries. So that is why we are actually more focused on providing the research paper, the thesis, which are primarily relevant to our field of marketing, our field of study, which we are doing through YouTube, which we are doing through our channels. You can visit our aerospace engineering channel as well for different concepts as well related to this field from graduate to postdoc level. And also we deal in some we can say chartered accountants channel as well, so you can go through and ask for the link as well, and we can provide you the details. But right now, just going through this extract of a piece of research paper, or actually by the research organization. So let's see what it's all about. An experimental investigation has been conducted to evaluate boundary layer separation control on a two-dimensional single-flip three-element high-lift system at near flight RE with small surface-mounted vortex generators. The wind tunnel testing was carried out in the NASA Langley Low Turbulence Pressure Tunnel as part of a cooperative program between McDonnell Douglas Airspace and NASA Langley Research Center to develop code validation databases and to improve physical understanding of multi-element airfoil flows. The article describes results obtained for small sub-boundary layer vane-type vortex generators mounted on a multi-element airfoil in a landed configuration. Measurements include lift, drag, surface pressure, wake profile, and fluctuating surface heat fluxes. The results reveal that vortex generators as small as 0.18% of reference, slat and flap stored, wing code, and micro vortex generators can effectively reduce the boundary layer separation on the flap. The micro vortex generators are hidden inside the wing when the flap is refracted, thus extracting no cruise drag penalty. Introduction: the performance of high lift systems on subsonic transport aircraft plays a major role in determining field length, required payload range capability for a given field length, and the noise footprint in the airport area during takeoff and landing. High lift systems have traditionally been mechanically complex, generally consisting of some combination of leading edge stalls and multiple trailing edge flaps. However, economic pressures are currently pushing modern transport designers towards mechanical, simple high lift systems with performance equal to or better than older, more complex designs, and current design objective is to reduce the number of flap elements from 2 or 3 to 1. The main channel of moving to single flap designs is to maintain high maximum lift values of a landing conditions without incurring boundary layer separation and the resulting performance losses. Flow separation on multi-element airfoils can be a complicated function of geometry in flight conditions and is not reliably predictable at this time. For example, previous reports have shown that certain high-lift configurations exhibit boundary layer separation on the flap. Low angles of attack is to employ flap-mounted vortex generators to enhance streamwise momentum in the flap upper surface boundary layer. The question is then to determine what are the smallest vortex generators that provide separation control and what are their aerodynamic cost. Conventional vane-type passive vortex generators VGs with device height H on the order of lambda have been used to increase near wall momentum transfer from the outer flow to the wall region. First introduced by Taylor, these vortex generators consist of a row of small plates or airfoils that project normal to surface and are set at an angle of incidence to the local flow to produce an array of streamwise trailing vortices. These vortex generators are commonly used to delay the boundary layer separation. Okay, so this is how it has to be explained. To enhance aircraft wing lift and to tailor wing buffet characterization at transonic speeds, a wide variety of VJs are in use and small large aircraft employ them for separation control. Many applications, however, be relatively large VJs that cause residual drag through conversion of aircraft forward momentum into unrecoverable turbulence in the aircraft wake. By reducing the height of conventional vane type vortex generators to only a fraction of lambda, vortex generators can still provide wallward momentum transfer over a region several times their own height, especially in high Rayleigh numbers. Boundary layers, for example, various sub-lambda scale vortex generators were recently shown to significantly reduce the flow separation of a backward-facing ram. Although sub-lambda separation vortex generators such as Wheeler's wishbones have been shown to control laminae separation bubbles as low Rayleigh number, only vane-type VJs were selected for this investigation since they have been shown to be equal to or better than the Wheeler type in controlling turbulent boundary layer separation. Furthermore, these vane type separators are lighter, less bulky, and can be relatively easy to manufacture in large quantities at NASA Langley. The objective of the present study was to determine the smallest VJs that would reduce or eliminate separation on a system on 2-3 single flap 3D high lift system and near flight Rayleigh numbers.